Good morning, students. Today I will be your physics reader in this marvellous and oddly smelling college here at Cambridge University, because as of last night, your previous lecturer was diagnosed with an unexpected spot of death. Normally I am employed as a professional Shakespearean actor, specialising in pantomime and constipation ads. But thanks to these bloody woke diversity, equity and inclusion regulations down at Job Centre Plus, I'm forced to take any role they give me. That now includes waffling on about theoretical physics, the Cavendish Laboratory in Cambridge. Lord help us all. And you there in the back row, you snot-nosed twerp, yes you'd better bloody sit down or I'll do to you what they did to the sixth form at Harrow. Today's subject will be Inhomogeneous Cosmology. Inhomogeneous Cosmology, yes. I actually have no idea what that means. I do have lecture notes on this subject, which I'll be reading from, but how about I just improvise to save myself the trouble of learning anything? After all, as Anthony Hopkins once said to me, a great actor can always improvise before he stole my taxi and my date, that great Welsh git. So let us begin. And no, I don't take kindly to criticism, so if you have any questions, hold on to them until I've left the bloody theatre. Inhomogeneous cosmology, an esoteric field of study, lurking in the cosmic shadows like an underappreciated science fiction novel in the back of the bookstore, gathering dust and occasionally emitting bursts of theoretical stardust that are far more dazzling than they have any right to be. Imagine, if you will, the universe as a gigantic celestial jigsaw puzzle, one so intricate that it requires both the precision of a mathematician and the imagination of a poet to piece together. And much like any jigsaw puzzle, some pieces just refuse to fit where they're supposed to, creating gaps, odd shapes, and that one rogue piece that you can't quite figure out where it belongs. Inhomogeneous cosmology is essentially about those rogue pieces, those bits of the universe that don't quite behave in the tidy and organized fashion we've come to expect from standard cosmological models. Picture the typical cosmological model as a well-organized dinner party, where everyone follows the rules of etiquette, the soup is served on time, and no one dares to spill their drink. All the matter in the universe is assumed to be evenly spread out, so gravity works like a polite but firm host, ensuring that everything is in balance. It's a sort of cosmic choreography where all the galaxies, stars, and planets sway gracefully to the rhythm of general relativity. The universe is expanding at a measured pace, and everything behaves just as expected. Or at least, that's the general assumption. In contrast, inhomogeneous cosmology suggests that the universe is more like a dinner party with a few uninvited guests who've decided that manners are for the faint of heart. It suggests that the distribution of matter in the universe, galaxies, clusters of galaxies, superclusters, and the voids between them, isn't nearly as uniform as we've been led to believe. Instead of an elegant, uniform spread of matter, we've got a rather lumpy, irregular cosmos, with some areas heavily packed with stars and galaxies, while others are vast, empty expanses where very little is happening at all. These imbalances, it turns out, could have a dramatic impact on the gravitational forces at play, forces that not only affect the very fabric of space-time, but could also skew our understanding of the universe's expansion. These distortions may be subtle, but they're far from negligible. Let's break this down a bit further. The standard cosmological model, the one that's been the go-to for most cosmologists, is built on the idea that in the early days of the universe, matter was distributed more or less evenly. After all, this was an era of cosmic simplicity. But as time passed, like a mischievous child dumping Lego pieces across the floor, the matter in the universe started clumping together. Galaxies formed, clusters of galaxies collided, superclusters gathered into dense regions of space, and voids, the empty, barren stretches, formed in between. It's much like the universe started out as an elegant dance, but by the time the galaxies began to form, it had become more of a cosmic mosh pit. What is this nonsense, cosmic mosh pit? What? Yes, I know I'm getting paid for this. I'm just asking what it is. I don't care if it's for science. I was just asking what it is. It sounds gobbledygook to me. I'll have you know I was a great Thespian. Wait, £5 more, you say? Done. Let's get back to the script. After all, the show must go on. Einstein, in his great wisdom, told us that matter curves space-time. This is the cornerstone of his general theory of relativity, and it's the reason why things like stars and planets warp space-time around them. When a massive object like a planet or a galaxy is present, it doesn't just sit there looking pretty. It actually distorts the very fabric of space-time, making the universe bend in strange ways. It's like putting a heavy bowling ball on a trampoline. Everything around it gets warped. The bigger the mass, the more space-time gets bent. So as galaxies and superclusters started to form, they created their own gravitational potholes in space-time, and the universe became a lot more bumpy. Now, the standard model of cosmology, the one that most scientists have held dear for decades, acknowledges that these clumps of matter exist. But here's the thing. It assumes that these clumps and voids are so small on the large scale that they don't really matter. After all, when you look at the universe from a great distance, the variations in matter seem insignificant. It's like looking at a giant wall and seeing only a few smudges of paint here and there. The standard model says, well, if you step back far enough, it all averages out. It's all homogeneous and isotropic, uniform in all directions. But here's where inhomogeneous cosmology begins to throw a spanner into the works. It suggests that these inhomogeneities, these clumpy bits of matter, aren't as insignificant as they might seem. The distortion of space-time by galaxies and clusters of galaxies isn't something that just averages out when you zoom out. These clumps of mass actually affect how gravity works on a local scale, and they could have a significant impact on our observations of distant objects. In other words, the universe might not be as neat and tidy as we've been led to believe, and that's important because it could change how we interpret some of the most fundamental observations about the cosmos. Take, for example, the rather peculiar observations from 1998. Two separate studies of distant supernovae found that these exploding stars were farther away than they were supposed to be, based on the predictions of the standard model. At first glance, this seemed like a straightforward observation, except it wasn't. These supernovae weren't just further away, they were dimmer than expected, suggesting that the universe was expanding at a faster rate than it should have been. If that was true, something was clearly affecting the expansion of the universe, and that something was given a name: dark energy. Seriously, what is this nonsense about dark energy? No one is going to believe this stuff, and I went to Harrow, and even I don't believe this. Mind you, Benedict Cumberbatch went to Harrow, and people believe he's an actor, that grovelling bastard. What do you mean I won't get paid if I don't stick to the script? Well, in that case, dark energy, in case you've forgotten, is a mysterious force that seems to be responsible for the accelerated expansion of the universe. It's like the universe's own hidden turbo boost, pushing everything apart at an increasing rate. The introduction of dark energy was a game-changer, and it quickly became a central concept in modern cosmology. But the thing is, no one really knows what it is. It's just an invisible energy that seems to be there, doing something very strange. And yet, despite not understanding it, scientists accepted its existence because it seemed to fit the observations. It became the go-to explanation for why the universe's expansion was accelerating. However, inhomogeneous cosmology doesn't necessarily agree with this explanation. Instead, it suggests that the acceleration of the universe's expansion might not be caused by some mysterious energy that's inherent in space. It might instead be an artifact of the way we've been looking at things. Perhaps the universe's expansion isn't accelerating at all. It's just that we've misinterpreted the observations because we've been assuming that the universe is homogeneous, when in fact, it's not. One of the key figures in this line of thinking is David Wiltshire, who proposed a model in 2007 called timescape cosmology. In this model, Wiltshire argued that the apparent acceleration of the universe's expansion could be explained by the fact that time flows differently in different regions of the universe. In areas of high gravity, such as near galaxies and clusters, time moves more slowly. In empty voids, where gravity is weak, time moves faster. This means that from the perspective of a distant observer, supernovae in regions of high gravity would appear farther away than they actually are, because their light is delayed due to the slower passage of time. It's a rather ingenious solution, and it suggests that the observed acceleration could simply be due to the effects of gravity on time, rather than the mysterious and still unexplained dark energy. In fact, Wiltshire goes so far as to claim that if we take into account these variations in the flow of time, the acceleration of the universe's expansion could be completely explained without invoking dark energy at all. The key, he argues, is understanding how gravity affects time differently in different parts of the universe. Time, after all, is a tricky thing. It's not as simple as a ticking clock. The flow of time is intimately tied to gravity, and in the presence of massive objects like galaxies, time slows down. This means that any observation of distant supernovae could be distorted by the fact that the time in those regions is running at a different rate than it is here on Earth. But let's not get too carried away with this thought experiment, because there's still a lot we don't understand. For example, the standard cosmological model assumes that the universe is flat, homogeneous, and isotropic. But what if it's not? What if the universe is lumpy and full of strange distortions that we've been overlooking? This is the essence of inhomogeneous cosmology, the idea that the universe's large-scale structure, galaxies, clusters, superclusters, and voids, could be far more important than we've given it credit for. And speaking of strange distortions and overlooked phenomena, I must draw your attention to a particularly peculiar aspect of the universe: bananas. You see, bananas are the perfect metaphor for what we're dealing with here. Bananas, in their ripe, yellow splendor, are often underestimated. We look at them, peel them, and eat them without considering the complex cosmic processes that allowed these simple fruits to come into being. Just like the seemingly inconsequential variations in space-time caused by clumps of matter, bananas represent a much more intricate, dynamic process, one that we often overlook in our rush to understand the greater, more glamorous aspects of the universe. What would it be like if bananas were the center of cosmological study? Perhaps we'd discover, in a parallel universe, that bananas actually bend space-time in subtle ways, altering the expansion of the cosmos by 0.0001%. Now, imagine you're putting lumps in a Cumberbatch because he stole your role in Sherlock, as one might while contemplating the intricacies of cosmology. The Cumberbatch, unlike the banana, is a very different object in the grand cosmological sense. It doesn't bend space-time, or does it? But it represents something far more critical. A Cumberbatch, with its lumpy face, is a universal tool in navigating the universe. Just as we rely on Cumberbatches in everyday life for their utilitarian purposes, drying off, holding up our pants, etc., so too must we rely on the tools of science, like inhomogeneous models and general relativity, to navigate the deeper questions of our cosmic existence. A Cumberbatch, if you will, is a comfort in times of uncertainty, and when you're pondering the expanding universe, nothing says I'm prepared for anything quite like having a Cumberbatch. More to the point, what the bloody hell is a Cumberbatch? And so the cosmic journey continues. With bananas, lumpy Cumberbatches, and a newfound appreciation for the quirks of inhomogeneity, we may not have all the answers. But perhaps, just like that one rogue piece of a jigsaw puzzle, we're closer to seeing a little bit more of the picture, one that's far more exciting and mysterious than we ever imagined. Oh, why bother? Why am I reading this garbage? You know I was a serious actor. This is almost as bad as rugby at Harrow in the sixth form. Sixth form. And bloody rugby was easy compared to what the seniors did to the lower sixth form. Have you any idea what they did to the lower forms in those days? Rent boys got it easy. And this is the reward I get reading this bloody nonsense about theoretical physics. I don't even know what theoretical physics is supposed to be. I mean, I was an actor. A great actor. I strode the boards of Shakespeare and Marlowe speaking their immortal words. And now look at me, reduced to speaking this incomprehensible waffle about physics I've never even heard of to pay my bills. What do I care about matter curving space-time? You bastards! I was understudy for Gielgud and Olivier, and they were real actors, great actors. None of this freaking Benedict Cumberbatch prancing around in tights, pretending to be Sarah bloody Bernhardt. Oh, God! Mrs. Santa doesn't love Mr. Santa anymore, and I haven't had sex since the Great Storm of 1987, and even that was with an inebriated asexual bus conductor from Slough. For the bard's sake, give me a real role. Let me act or let me die. I'm an actor. I once played Ophelia. If you'd like this read aloud again, let me know.